Hello, everybody. Welcome back. Couple things. So we're coming up on exam 3 next week, in case you didn't know.
So how your speed run 5 sections?
It's a good question. So the thing is, exam 3 will only cover up to 3.5. So hopefully we'll be finishing 3.5 today, if not like basically starting getting through most of it. And then we're going to skip 3.6. 3.6 doesn't matter. It's a fun section if you're curious about it. It has to do with a very, very archaic practice that we use in mathematics, including sacrificing a chicken. But differentials are not very, very important. So we're going to skip that. And then 3.7 is not really related to any of the other stuff that we're doing here. It's called antiderivatives, and that's really a precursor into unit 4. So we will just press on. And the exam review we posted a little bit later, either today or tomorrow. So be on the lookout for that. And once that's posted, have at it. And have a grand old time. Do you want your? So anybody have any questions about exam 1 or sorry, exam 3 rather? All right, so let's go ahead and get started. So we were talking about curve sketching last time and being able to take all the things that we've learned about how to find increasing, decreasing, concave up, concave down, and all that stuff, and bring that all together to create a graph. So last time we didn't get to finish this picture, but we did get everything we needed. So we found the domain because it was a polynomial. It was defined everywhere. We found our x-intercepts, if they can be found easily. If they can't be found easily, don't worry about it. And then we found our y-intercept, which happened to be one and the same. Then we found the first derivative to do the first derivative test, determine where the relative maxima and minima were, and then also the places where it was increasing and decreasing. And then we found concavity and then potential inflection points, which this function had 2. We didn't actually get to locate the, we didn't finish that portion of it. So let's go ahead and finish that now. So it is concave up between negative infinity and 0, and then from 2 to positive infinity, and is concave down from 0 to 2. And then we had inflection points at both 0 and 2. Because this is a polynomial, it's defined everywhere. So P of 0 and P of 2 both exist, meaning that they are inflection points. That's what you need for an inflection point. The concavity needs to change, and the function needs to be defined there. It needs to be continuous more aptly, but most of the time, that's always going to be the case. So P of 0 is 0, and P of 2 is going to be negative 16. So we have inflection points at 0, 0, and negative and 2 comma negative 16. Actually, I need more space, so I'm going to put those here. So 0, 0. And then 2 comma negative 16. So what we're going to do is we're going to, now this is an arbitrary graph. So notice that the inflection point is 2 comma negative 16. That is really, really low. That's a lot of tick marks. So we're going to make each vertical tick mark worth, let's say 5. So each, and that also is further confirmed by the fact that we have a relative minimum at 3 comma negative 27. So we're going to need to have our bottom at least go to like negative 30. So we'll make each one of these tick marks. Let's use blank. 5, 10, 15, 20, 25, 30. Negative 5, negative 10, negative 15, negative 20, negative 25, negative 30, and so on and so forth. But all of our critical values are pretty well localized, 0 to 3. And so we can leave the X scaling the way it is. So let's go ahead and plot all the important points that we've created. So we had critical value, we had intercepts at 0, 0 and at 4, 0. We had an inflection point at 0, 0 and then at 2, -16. So 5, 10, 15, right about there. And then we had a relative minimum at 3, -27. So roughly, right. So 5, 10, 15, 20, 25, 30. So a little bit above the 30, right about there. Good enough for me. Let me zoom in on the graph only. Let's get that going. So we're going to go ahead up and set up our little cheat sheet down below and then use kind of dotted lines to help us out. So we'll draw 2 lines. This is going to be the F prime line. And then right below it is going to be the F double prime line. Now the critical, like the important values that we had to divide up our interval for increasing and decreasing were 0 and 3. So let's go ahead and put 0 here and 3 here. And we had that it was decreasing, decreasing, increasing, decreasing, decreasing, increasing. And then for concavity, we only had the values 0 and 2. So we'll plot those. And then we saw that it was concave up, concave down, and then concave up again. Let's go ahead and make some lines to break this up into pieces and try and figure out the shape of the graph based on this information. So you can draw that little cheat sheet if you want. If you remember what it would look like, it looks like this. So you have like that. Is there a question?
If 2 to 3 was concave.
2 to 3. Oh, so great question. So 2 to 3, it will be concave up. So notice like this. In this portion, you're decreasing and concave down, but then after 2, you're still decreasing, but you're concave up.
Oh.
So that's how we read this graph. Or not this graph, but this little chart. So if we're decreasing in the first little subsection, decreasing, that means we're either this one or this one. But we're concave up. Which one of those is concave up? The first or the second? The first. So our curve should look like this to start off with. Now, that doesn't mean that it's going to be this nice, perfectly sloped thing. It could be very, very slightly bent. And you'll see that's what it's going to look like. Draw these things with light pencil. Draw it with light pencil when you start off with. Seriously, do not bring a pen to this exam. It's just going to screw you over. Like you can draw it with a pen later on, but bring a pencil so you can just draw it lightly so you can get it all squared away. And you can make mistakes. From 0 to 2, it is concave down and decreasing. So that's going to be this shape here because you're decreasing concave down. So your shape is going to be like this. Then you're going to be decreasing and concave up again. So it's this shape again. And then increasing concave up, that's going to be this one right here. And that's the way you can use that little chart as a cheat sheet, or you can think about here's a happy face, here's your concave up. What side are you would your graph be increasing on? Like this is the way I didn't learn about this thing until one of my students showed me it. When I was in grad school. But if you're looking at something that's concave up, right, like this, right, in purple, when is it concave up and increasing? On this side. Because you're still concave up, but your tangent lines are positive. Whereas on the other side over here, your tangent lines are negative. So that's the way I did it when I was a student. And we know that this right here is going to be a relative min. So we know it's going to be kind of a slope there. We can kind of add that in just so we know about it. So now that we have our relative shape, let's scroll back up a little bit and get to our picture. And so we need it to bend down all the way to this thing. So we're gonna, and then as we suggested before, let's use gray, and we'll do dotted lines for a second, dividing up our interval into pieces to help us out along the way. All right. So we're gonna be concave down. So we're gonna be coming up from the top left downward. And then it's it's a point of inflection. So it's gonna come down, gonna bend, and then it's gonna switch to being concave down. And then it's gonna switch it's gonna switch again here. Hard. Sometimes you have to draw it several times. And back up. And I didn't draw that middle part better. I want to draw it better. So I'm going to erase it and start over again. I'm showing you this for a reason, to show you that it's not perfect. You can draw it a million times and still not be happy. So I wasn't happy, so I'm going to start again. Stop that. Indeed. There we go. Not perfect, but you can see that at 0, or sorry, at 2, it does go from being bent downward to bent upward. I'm happy now.
Kind of like Yoda there for a second.
Thank you. Let's go for that. And that's our picture. Boom. And that's how I won my wife over. So that's
Very nice.
Question.
yes, go ahead.
Is there something that's preventing the beginning, like going into negative infinity? Like, why is it stopping at -2? Or you just don't like it?
Yes, great question. Great question. So Trevor asks an excellent question. Why did I make it kind of stop here? So it's not that it has a vertical asymptote at 2. It doesn't. It's just by doing this enough times, I notice when the steepness is going to be very, very large. So, but I've had students do something like this. And you can do that. I do not care about actual points. Besides the points that we find from increasing, decreasing, or like relative extrema and intercepts and inflection points. I don't care how steep you make it, how wibbly wobbly you do it. It's fine with me. So that, like, if you drew this graph that I'm going to do in red for a second. Still get 100%. Still get 100%. Yes,
So,
second question.
I know when you were looking for inflections, you used both the CV 0 and 2, but at the top, when you were figuring out the X values, you only plugged in the 0. Is that because it would make it simple instead of using 4?
Sorry, say that one more time.
So the X, when you figured out the X and Y intercepts at top,
Yes.
you only used a 0 plugging into the original equation. Is
For-
that because for simplicity?
For the y-intercept?
Yeah.
So the y-intercept, for a function, you only have one y-intercept, and it's always when x is equal to 0. Because that's where it's going to cross the y-axis. So you only need to test one value, like you only need to find one value for the x-intercept, or for the y-intercept.
What if we would have used 4? We would have still got. Like, no. for
Oh,
X, if you
excellent.
put you put P of 0, 0 minus 0 equals 0, but what if you did P of 4? Then you plug that into to get a y-intercept.
So the y, oh, so okay. So 4 doesn't give it like that was going to give us an x-intercept. To find the like x-intercepts and y-intercepts are done separately. It just so happens that here, because 0 is the only place that has an x-intercept that is both an x-intercept and a y-intercept, we had to do it twice. But we weren't computing p of 0 to find the x-intercept. We were using it to find the y-intercept. Does that make sense?
Yeah, no, that's what I'm saying.
Oh.
Like, if you use the x more in the original equation, it would have given you a whole different y value.
It should give you 0.
Oh, it would have?
Yeah, because by definition, the y-intercept the x-intercept will have a y value of 0.
Sorry.
No, very like it's important. So there we have it. Super cool. And then if you want to, you like if this was on an exam, you can absolutely leave those slight dashed lines or faint vertical lines to help you figure out how to preface it, but it's not. But if you want to make it pretty, you can erase them, which is what I'm going to do. Boom. Any questions on that? Does that chart at the bottom start to make more sense now that we've seen it in a couple circumstances? Okay, let's do another one. Now, we are going like this with curve sketching. This is where we need to simplify. We need to simplify our derivatives along the way. So this function, because I know I'm going to have vertical asymptotes, right? It's a rational function. The vertical asymptotes will happen where the denominator equals 0. Let's go ahead and write this in factored form at the same time. This is 3x squared over x plus 1 times x minus 1. So intercepts. I guess domain we can write over here. So the domain is going to be negative infinity to negative 1 union, negative 1 to 1 union 1 to positive infinity. And that's because the function is only defined where its denominator it's undefined where its denominator will equal 0, and that would be at 1, negative 1. So those are the only 2 points where this function is undefined. Everywhere else, this function's nice and neat. So, any questions on that so far? On that domain? X-intercepts. We're going to set the function equal to 0 and find the x values that make that happen. So 3x squared over x squared minus 1 equaling 0, that just gives us that x is equal to 0. Because the only place where this would equal 0 is where the numerator would equal 0. And 3x squared equals 0 implies x equals 0. So this function is going to be the same thing. So that's your x-intercepts. Your y-intercepts. You're going to find f of 0, which just ends up being 0 as well. So there's only one intercept at 0, 0. And I'm not going to box it in, but I am going to underline it. It can really help you to have all that information kind of highlighted so you can just gather it all instead of trying to parse through all of your information to find every little detail that you've given. Then we got the intercepts, we got the domain, we still need the asymptotes. We didn't check for those in the previous one because it was a polynomial, and polynomials do not have asymptotes. Rational functions can. Not all of them, but a lot of them do. So asymptotes. The VAs are going to come from the denominator. From denominator, denom, equaling 0, you get x equals 1 and negative 1. So we're going to have 2 vertical lines at 1 and negative 1. And then a horizontal asymptote. Where do we have a horizontal asymptote? Or do we have one? So horizontal asymptotes, if you want to do it the calculus way, you take the limit as x approaches positive infinity and negative infinity. And in this case, that would be, so looking at 3x squared over x squared, same power. So it's going to be 3. But you can also do it by looking at the ratio of leading coefficients. Since they're both degree 2, it has a horizontal asymptote at y equals 3. by looking at degrees of the numerator and denominator. We get y equals 3. And just as a reminder on that one while you're writing it down, so the reason why that's the case, the reason why I can just look at this and say that it's going to be 3 is imagine horizontal asymptotes. It's been a while since we talked about them, but they talk about end behavior. What's happening as x gets incredibly large. And so as x gets incredibly large, that -1 does not matter. So virtually at the ends, the function just looks like 3x squared over x squared, which is just 3. So that's why we know that it's going to be 3. All right. Now we look for increasing and decreasing in relative extrema. So increasing/decreasing, unless there's any questions on anything we've done so far.
Wait, can you just repeat how you got that first one?
Sure. So students asking me, Leslie's asking me how I found the asymptote, specifically the horizontal asymptote. So I was looking at the degrees of the numerator and the denominator. That's doing the old way, the old-fashioned way, which is from Math 126. And you can also look at some videos on that one, finding horizontal asymptotes of rational functions. I believe in the algebra and pre-calculus review section on our Canvas page, I do have like Eric Hutchinson and my wife's videos on how to find those things. But you could also do it by saying, okay, what's the limit as x approaches positive infinity of f of x? And I guarantee you, if you do that, you will get 3. And since the limit as x approaches infinity of the function equals 3, that's a finite number, so that's the horizontal asymptote. Y equals that number. Yes, Kat.
How do you get that horizontal asymptote using the degrees?
So they're the same degree. So that means that they're increasing at the same rate. So if you have the degree of the numerator and the degree of the denominator are the same, then the horizontal asymptote will be at the ratio of leading coefficients. So 3/1, which is 3. Yeah.
But if they were different.
If they're different, so there's a rule about it. If you have, if the degree of the numerator is less than the degree of the denominator, so like you have x to the first power over x to the third power, or x to the 17th over x to the 21st. So if you're if the degree is bigger in the denominator, you have a horizontal asymptote at y equals 0. If they're equal, HA at y equals ratio of leading coefficients. And then if the degree of the numerator is larger, so we're talking about like x squared over x, or x to the 15th over x to the 3rd, or something like that, then there's no horizontal asymptote. That's the rule in an abridged version. So now we got all that way. Let's go ahead and find increasing, decreasing, unless there's any other questions. So f prime, I'm gonna do the chain rule. Sorry, the quotient rule. So 6x times x squared minus 1 minus 2x times 3x squared, all divided by x squared minus 1 squared. Which ends up being, if you simplify it, that's 6x cubed minus 6x minus 6x cubed, all divided by x squared minus 1 squared. And isn't that nice? The x cubed cancel, so we don't have to deal with a cubic. Cubics are no fun. Ooh, we're running out of space, aren't we?
Are we not?
What?
When are we not running this space?
Fair. Always a lot of math. So this is negative 6x over x squared minus 1 squared. So Yes, it's x squared minus 1 squared. So you could write that as x plus 1 squared times x minus 1 squared. But we're going to save on space and say that the critical values, well, the important values are going to be the IVs are going to be x equals 0, 1, and -1. 0 from up in the top, that'll make the function equal to 0. The derivative equal to 0. And 1 and -1 will make the derivative undefined. Does not exist. But only this 0 is the only CV. Because f of 1 and f of -1 do not exist. They're not in the domain. But they will play a role in whether the function is increasing or decreasing. And that's why we include them. That's why we find them. So let's make our sign chart. F prime. Here's -1. Here's 0. Here's 1. And the good news is, so let's just pick x equals -2, x equals -0.5, x equals 0.5, and x equals 2. Sadly, we didn't get to choose a nice integer number, but you know, fractions and decimals are people just like you and me, so we gotta use them every once in a while. We gotta bust them out. And the good news, though, is that x squared minus 1 quantity squared is always positive, right? Because the quantity is squared. No matter what happens, it's always going to become positive. So the only thing we're really looking at is the numerator. So it's always going to be positive down at the bottom. Then that -6 is always playing a role. And I mean, you can keep it in like you can take it into account when you plug in -6x. I just like to treat it as a separate entity, just so that I know that it's there. But to each their own. Plugging in -2, x will be negative. So we've got 2 negatives up top and a positive down bottom. That means it's increasing here. If you plug in -0.5, it's also going to be negative. So it's going to be positive here. And then if you plug in 0.5, x is going to be positive. So we've got 1 negative. So we're decreasing. We're negative. And the same thing here, negative. So increasing from -infinity to -1, comma, -1 to 0. Decreasing from 0 to 1 and from 1 to positive infinity. No relative minimum, because there's no place where it goes from going down to up. Relative max at 0, 0. That relative max right here. And no relative min. Yes. All right. Totes chill. We all on the same page? Because like if you're on a different page, you're not doing the same thing. Oh, okay. Until I was 22 to understand why they're called evergreen trees.
They're always green.
Because they are evergreen. Exactly. Didn't realize.
I went to my friend Eric, that they were early friends, so we're about to. They didn't like it.
Curiosity killed a cat because of Schrodinger's box.
Yes. Yes. Schrodinger's good old Schrodinger's cat.
Furniture is a killer.
That what?
Furniture is a cat killer.
Eh. I mean, the cat kind of did it to itself. Okay. Sorry. So concavity is next. So F double prime. Now we're going to use the I could have factored it up above. Sometimes you'll need to do that. Sometimes it ends up being that the denominator looks different. But you want to use the most simplified version when you're finding the next derivative. Otherwise, it's just going to be a massive mess for you to, and headache. So we're going to use the bottom version of it, the most simplified version that we have. F double prime of x is going to be -6 times x squared minus 1 squared minus 2 times x squared minus 1 to the first power times 2x times -6x, all divided by
Bless you.
x squared minus 1 squared squared. And I would like to skip the algebra, but I think it's important to kind of go over this one just because we haven't done that too often. So you're going to get, oh, here's the trick. Here's a trick to help you simplify it faster. Because we could absolutely FOIL out that x squared minus 1 squared. We could do that. We could. And it wouldn't be wrong. It would just be making the work way harder on yourself, because you notice that in the numerator, there's a common factor of x squared minus 1. And the denominator is only x squareds minus 1s. So we will be able to factor that out and cancel it right now. So what we're going to do, x squared minus 1 out front. And now we've got -6 times x squared minus 1 minus 2 times 2x times -6x. All divided by x squared minus 1 to the 4th. And remember, it's not to the 4th because of 2 plus 2, it is 2 times 2, which I know is the same thing, but like it's important to remind yourselves that power raised to a power, you multiply the powers. If that had been x squared minus 1 squared to the 3rd power, it would have become x squared minus 1 to the 6th. Just so we're clear. And so we cancel one of those factors. We'll do a little more simplification. -6x squared plus 6. That's going to be 4 times 6 is 24. So plus 24x squared. All divided by x squared minus 1 cubed, which ends up being 18x squared plus 6, all divided by x squared minus 1 cubed. Yes.
Did we cancel out both x squared minus 1? Because you have an x squared.
What line? Second or third?
Second.
Line. So we factored out one of the, so they only have one factor of x squared minus 1 in common. So I factored that one out. So there's still going to be one left over on the inside for the first term.
Okay.
The second term has it gone now.
And then going to the next line, how do you get rid of it?
So I canceled it down here. And then I distributed this -6 into both of these. And then I simplified this.
Got it.
So that's -6x squared plus 6. And then you got 2 negatives, so that makes it a positive. 2 times 2 times 6 is going to be that 24. And then the x times x gives the x squared. So, all right. What are the critical, like not critical values, but basically critical values and important values? What are they? Where are the points? Where are the x values where the derivative does not exist? The second derivative does not exist, and where it's equal to 0. 1 and -1 only. So f double prime equaling 0 / d/e implies x equals 1 and -1 only. Notice that the numerator is a sum of squares. 18x squared plus 6. That's never 0. Sum of squares, right? Sums of squares never equals 0 because you're taking a number that's positive, 18x squared, it's always going to be greater than or equal to 0, and you're adding 6 to it. That's just going to make it always positive. There's no way unless we start working with negative complex numbers. Yes. Double prime. Yes, f double prime. I realize, like, you guys can't. That's clearly 2 lines. Sierra, that's clearly 2 lines. Why are you questioning me at all? Why are you questioning? No, I'm messing with you. I'm totally messing. Totally messing. You're very, very like that's very, very fair. f double prime equals 0. Thank you. Do it the other way?
Yeah, where you do it with the.
Oh, that would be for what was that for exactly? In certain contexts, yeah. Yeah. I forget what I was mentioning that in regards to. Was that in regards to 3.1? There's 3.3. Okay. Fair enough. Like d squared y dx squared, however you want to do it. So let's set up a sign chart with the limited space that we have. -1 and 1. Keeping in mind now, x squared minus 1 is going to be to the third power, so we can't just assume that it's going to be positive or negative. However, the numerator is a sum of squares. It's always going to be positive, so we can just put a plus sign up in those ones. X equals -2, x equals 0, and x equals 2 should be sufficient choices. Positive up top for all of them, no matter what. I mean, you can verify it however you want. Plugging in -2, quantity squared would be +4 minus 1, that's +3 cubed, that's positive. So it's concave up here, you're positive and you're feeling positive, which means you got a smile on your face. Plug in 0, you get 0 minus 1, that's -1 cubed, stays negative. So it's negative. If you're negative, you're feeling down and you've got a frown, then you plug in 2 by symmetry, it's also positive here. So plus, and concave up, which means the smiley face. And concavity changes there. What are those inflection points? No, because the function is not defined there. So not inflection points because f of 1 plus or minus 1 d and e. Okay. Now I would write concave up, concave down. We're like, we don't have any space left, and we're only going to be using it to make the graph, so we don't need to list it down. So there aren't any. That's a good question. Let's graph and find out.
Wouldn't all inflection points be something that equals 0 d and e, because that's how we originally got those x values?
So like inflection points happen where that where it equals 0 or does not exist. But you have to also have the function existing there. If the function doesn't exist there, you can't bend the graph at all.
Because if it was just polynomial,
Then yes, if it was just a polynomial or an e to the something where, because e like exponential functions are defined everywhere, then yes. But because this is going to have vertical asymptotes there, there's no way to make it wiggle or jiggle free, as we say in Chicka Chicka Boom Boom. Yes. It's because we're dealing with the rational function. Kate and then Paul. Can I get quiet? Because you can't factor. It is a difference of squares. Sorry, it's a sum of squares. So sums of squares cannot be factored over the real domain. If you have x squared plus 1, the only way to factor that is x plus I times x minus I, where I is the complex number.
About 2.
Yeah, you could. You could, but it doesn't do anything. Like a valid point. You can factor out a 6 here, but since it's a +6, it's not going to change the sign at all, and it's not going to make it any easier on us. That's the like a valid point, and you're not wrong for factoring out a 6, but it's not necessary. If there was like an extra x that you could factor out with it, that might change some things. But because it's just a sum of squares, I'm not going to care about it. Yeah. But yes, I was misspeaking. Technically, you can factor it. Yes, you can factor out a 6. And Paul.
I lost my train of thought.
Happens to me all the time. If you remember it, let me know.
Oh, wait, yeah.
What does it say? Not if header points because.
Not inflection points, because f of plus or minus 1 does not exist.
Okay,
Not inflection, like, and that's fair. That's hard to read. Not inflection. It's not much better, but. All right. So let's go ahead and plot everything we need. For this one, since the y value, like all the points that we got were pretty well localized, 0,1, like 0, 0, is the only point we have actually. So that's nice. So we'll just plot 0, 0. We have vertical asymptotes at 1 and -1. So I want this to look a little bit prettier. So I'm going to make every 2 hash marks mean 1. So I'm going to make this 1 and this -1. And the reason for that, by the way, once again, is that imagine, if you will, if we were to make it just every tick mark, then when you draw this, you're going to have all 3 of your dotted lines in this little subsection. And it's going to be very, very tiny. So I'm going to space it out like that. So let's draw our 2 lines, one for f prime and one for f double prime. And so for f prime, we had 0, 1, and -1. And then for f double prime, we just had -1 and 1. Let's go ahead and split up our little thingy, whatever we want to call it, into 4 segments. It was increasing, decreasing. So plus, plus, minus, minus. And then it was concave up, concave down, and concave up. So you can either use your cheat sheet by making that little diamond thing, or you can do it by hand. If it's increasing and going to be concave up, it's bending upward, your curve is going to look like this before -1. Between -1 and 0, it's going to look like this. Going to be kind of an arced down. Then after 0, but before 1, it's going to be the mirror image. And then decreasing and concave up, that's like the left half of your smile. Like that. What I normally do first, and I didn't do it, what I should have done is I should have drawn my my asymptotes first. But I'm going to make every tick mark here vertical tick marks 1, increments of 1. It doesn't matter to do it in increments of 2. You could do that. It's not wrong. It's just, this is just going to make it look prettier. So let's go ahead and make these asymptotes. One at 1, one at -1. And then 1 at 3. A horizontal. A horizontal 1 at 3. Thank you. All right. And we got to use the we've got to use the fact that it's a rational function and asymptotes to our advantage. They hug their asymptotes. So we're either going to look like this in blue or this in orange. Which one do you think it is? The blue, based on it, like, and that's why we draw our little picture. Keeping in mind that you have to hug your asymptotes. So the function will look like this. And if you want to, you can go pedantic like this. If you really want to, that's fine with me. I would argue that it probably should look like this, but I'm not going to stop you from channeling your inner Bob Ross. The next piece. start up at the top or at the bottom? The bottom. Just purely based on like the way the graph works, we can't have that happen here. In order to draw this, if you're going from left to right, you start at the bottom and then move your way over. So it's going to look like this. And then it's going to go down. And then on the other piece, it's going to look like this. Oh. Okay. 0, the inflection did not change. 0 is a relative max.
You can cross horizontal, right?
Horizontals you can cross. Yeah. Sometimes you cross them, sometimes you don't. It all depends. Yes.
How come, so like on that last part,
Uh-huh.
how you did the top, how can, wouldn't it also work at the bottom, below that? What's
If
on the last one?
so, remember that at the end of it, you have to like. So we could try and start at the bottom, but then that would mean concave. That's concave down. Like easy thing to make a mistake. And so, sometimes the function will look, maybe it'll look like this. It might dip down below and then come back up, but ours can't do that because if I were to do that, yeah, there would be an inflection point right there. And there is no inflection point. So, but every once in a while that happens.
How would I know, like, if this didn't just start down here and go up, or this one did?
Okay. Good question. So how do we know, I'm going to erase this piece for just a moment. How do we know it doesn't, for this first one, doesn't go like this? Anybody want to answer? The horizontal asymptote. It has to hug that. So in order, we can. So, but the problem is this, because horizontal asymptotes have, like, you have to hug them, right? You have, like, like, the function will eventually become -3. So if you were to start down here, eventually it would need to come back up. But that would lead us to having a place where it was concave down when it's supposed to be concave up. Does that make sense? So when it comes to horizontal asymptotes, you know, you're gonna come like this or like this. And the only one where it's going to be concave up is the top one. Is that okay? Great question. Yeah, in the middle portions, like locally, but very ends, it should be leveling out. Yeah, like it could be that you have a dip here or here. Sometimes that does happen. I think in the exam review that I've got, I think that does happen in one of them. But it's just at the very ends of your graph. At the very ends of your graph, it should be leveling out. Great questions, guys. All right. Let's do another one. We're gonna skip the last one though. We're gonna do this one, but we're gonna skip the last one. I'll make a video on that one so you guys can see it. Just so that we can start up optimization and all the fun stuff that optimization has to offer. So this is a trig function. Well, it's not a trig function. It's an amalgamation of polynomials in trig. But the fact of the matter is, when you look at it, the domain. What's the domain? All real number. 0 to 2 pi. Actually, now that I think about it, we only defined it to be on 0 to 2 pi. I got ahead of myself. If it was the whole function, it was the whole thing, then it would be from negative infinity to positive infinity, because sine is defined everywhere, x is defined everywhere. But we already have our domain. There's not going to be any asymptotes because it's not going to have any place where you'd be dividing by 0. If it had tangent in there, tangent has vertical asymptotes. If it had secant or cosecant, those have vertical asymptotes. But sines and cosines and x's, no asymptotes. So the only thing we're going to be looking at are x-intercepts x minus 2 sine of x equals 0. Do you guys know how to solve that? It's that's one of those ones where this is where computers come in handy. There's not really an easy way to solve this by hand. To find the solutions of x minus 2 sine x equals 0. Very, very daunting task. It ends up being it's called like somewhere around 2 pi over 3. It's you'd need a graphing calculator to find this out or ask a computer. So no easy x-intercept. Sad face. There's no easy x-intercepts, and that's okay. So when you're doing these types of problems, the x-intercepts, the y-intercepts, they're mainly just there to help you get some points to plot. And if you can find them easy, great. If you can't find them, like give it the old college try. Look at it for about a minute. If you can't find them, move on. Y-intercepts you should always find though, if you can, because the y-intercept is very quick. G of 0. That's going to be 0 minus 2 sine of 0, which is going to be 0, because sine of 0 is 0. It's a lot of zeros, I've said. So that means we've got a y-intercept at 0, 0. That's also an x-intercept, but it wasn't going to be easy to find it. So we'll just skip that and just find the y-intercept that way. So we got that. Now, as an aside though, because we're working on a small interval, let's find the endpoints. Because we're working on the closed interval, let's find the endpoints. Is it necessary? No, but it definitely makes it look prettier. So G of 0 is still 0. And G of 2 pi, just to save you time, is 2 pi, which is roughly 6.28. So we have 2 pi, 6.28. Increasing, decreasing. We found we don't have any asymptotes, we don't have any domain issues. The only things we had were intercepts. Now we move on to the first derivative test. So increasing, decreasing. By the way, leave some decent amount of space down here. That's where we're going to draw our graph. The reason why I did not put a graph on here like I did in the other one, because we're going to be dealing with a trig function that's also got some polynomial aspects to it. So the values are not going to be very easily defined. So we'll see how to draw it in a second. So increasing, decreasing. Find g prime of x, which is just going to be 1 minus 2 cosine of x. And yay, we get to solve a trig equation. Love solving trig. Trig is always fun. It's very tricky, really hidden. As my son would say. G prime of x equaling 0 / d and e, though there's no place where it doesn't exist. It's well defined everywhere. We get 1 minus 2 cosine of x equaling 0. More aptly, cosine of x is equal to 1/2. So don't answer it out loud. Get everyone a chance to think, but you got to know your trig. When does cosine of x equal 1/2? Between 0 and 2 pi. That's positive, right? So it's in the first and fourth quadrant that the cosine is positive. 1/2, that's that would mean that your base angle is going to be the small one, right? It's going to be the small angle. So that's going to be the pi over 3. It's going to be the big angle, 60-degree angle. So pi over 3 and 5 pi over 3. Pi over 3 and 5 pi over 3.
I feel like this is the longest week ever. It keeps dragging, it's only Wednesday.
I get that. Thanks for telling me I'm awful. I get it. Thanks. Thanks. This class sucks.
Oh, it takes forever.
No, there's worse classes.
The thing, like, what I will give to you, Sierra, sorry to interrupt you, Elizabeth. What I will give to you is this is a very, very tedious section. Because there's so much information to gather. And it feels like a lot of hoop jumping. And so I get you, I get you. It's not always fun. So I'm not going to make a full number line chart because I only work on the interval 0 to 2 pi. But here's pi over 3, and here's 5 pi over 3. Oh, I want to bring those up top. Oh, wait, like, sorry, old habits die hard. Apologies. Pi over 3. So give anybody a cookie if they can give me the not really, I don't have any cookies. But
I was like, yeah, I'm gonna figure this out, I'm gonna get cookie, everything's gonna be fine.
Do you have those treats from last time?
He was like, throw them.
no, unfortunately, like I cannot well, I'm not gonna ask Elizabeth to make more stuff for us, but just throw them at you.
I got you.
So how do we figure out what points to test? How do I figure out the points to test? They're just values, exactly right. Now, we could do it if this was a class where I didn't allow you a calculator, this would be a pretty hard task. But there's an easy way. We need to know our trig, we need to know our unit circle. So x equals pi over 6, that's going to be a number that is less than pi over 3, but greater than 0. In between pi over 3 and 5 pi over 3, if you're looking at a unit circle, pi over 3 is right here, 5 pi over 3 is here. So you can choose any number. I would recommend pi. But you could do pi over 2, you could do 3 pi over 2, anything you want. So I would recommend pi. And then here, x equals 11 pi over 6. That's the only real nice number that you have. Well, I mean, I guess 7 pi over 4. Now, that being said, since we're allowed a calculator in this class, you could find out what the approximation of 5 pi over 3 is. It's roughly going to be around 5-ish. And so so you could like choose x equals 5.7 and x equals 3 and x equals 0.1. That would all do, and then plug it in directly. There's no factors here, so we're just going to have to do it by hand. But however you want to do it is fine. You're allowed a calculator in my class, so use it to your advantage. When you do it, you'll plug in and you'll get negative here, positive here, and negative here. So it's decreasing, then increasing, then decreasing.
So to get this straight,
Yes.
x equals pi over 6, x equals pi, and x equals 8 pi. over 6.
11 pi. That's a hard one to see there. It's 11 pi over 6.
Okay.
It does look like a bunch of lines. Well, when you look at it like that, though. All right. So that's the increasing, decreasing. Then we've got to do, we notice then that we have a relative min and a max. Just to save on time, so g of pi over 3 is going to be approximately negative 0.68. So we have pi over 3 comma negative 0.68. And then g of 5 pi over 3 is going to be approximately 6.97. So we have 5 pi over 3 and then 6.97. And I'll tell you why once we get to the graphing portion, why I'm using the approximation there. Another reason why I'm using the approximation there is what you're going to end up having with all of our x values, all of them are radians. All of them are nice angle measurements, right? Every single thing we've had has been a nice angle measurement. Pi over 3, 5 pi over 3, 0, 2 pi. All those things are nice. Whereas once you start plugging it into the function, you get something like 5 pi over 3 minus 2 cosine of 5 pi over 3, which is 2 sine of 5 pi over 3. It's a very, very nasty number because it's not just pi's, it's also radicals. It's awful. Might as well find the approximation to plot that point usefully. Yes.
Is there a reason why we're getting the actual location of the points instead of just showing on the interval where it's increasing and decreasing?
Yes, because we're going to be sketching the curve, so we want to know the location of those relative extrema.
Did we not need that on the previous problem?
We only had one relative extreme on the last problem. We only had 0, 0. But if you look back on the, we only briefly talked about it, but on this one, we did find the relative minimums and the inflection points. So. Concave up, concave down. Concavity. You've got g double prime of x, which is going to be 2 sine of x. So setting the second derivative equal to 0, this one's a quick one. This one's a quickie. It's a quick derivative. Shouldn't have said that. That I did not. Get your heads out of the gutter, guys. Get your heads out of the gutter. I was just making up words. I was projecting word vomit.
Okay, Mrs. Rose.
Okay. This is a quick trig equation to solve. When does sine equal 0? 0 and every multiple of pi. So x equals 0, pi, 2 pi, and those are the only ones that are in our interval. We don't really need to test 0 and 2 pi because they're at the very outskirts of our intervals. We can do it, but it's not going to be useful. So we'll set up our sine chart. Once again, stopping at 0 and 2 pi, and the only thing in the in-between is pi. And we can pick any number we want less than pi and any number that we want greater than pi. I would recommend pi over 2 and 3 pi over 2, especially since we're dealing with sine, and sine is very nice at pi over 2 and 3 pi over 2. So x equals pi over 2 and x equals 3 pi over 2. 2 sine of pi over 2, that's 2 times 1, that's 2, so it's positive. And we're concave up here. Got to smile. 3 pi over 2 sine is -1, so it's going to be negative there. And so you've got that. Now, just as a reminder, though, I realized this as I was talking about this one. So you can use your calculator, and like if you don't want to find a nice trig special angle, you can just plug in like x equals 1. But make sure that your calculator is in radians. For this class, we never deal with degrees. We never deal with degrees. We're only dealing with radians. So make sure that your calculator is in radian mode. And if you're ever uncertain of that fact before any quiz or exam, just let me know and I can help you out with that. Yes.
In the previous notes, when we did the increasing and decreasing, we also
Wrote.
did little downs between.
Oh. Yes. I did it very quickly at the end. Thank you for Nope. Yeah, it's just to tell us, like, it's a way that I like, for me, it visualizes in myself, like that, like, if I was to trace the curve, it would look like it had a slope there or a hill at pi over 3 or 5 pi over 3 and a valley at, that is correct. Yes. So absolute extrema, just as an aside, absolute extrema, it's very rare that you can, like, most functions that we encounter don't have absolute extrema globally. Because most functions end up looking like something like this. And so they go all the way up towards infinity. So like if you were looking at it globally, the whole thing, there's no maximum value because it just keeps going up and up and up. But once you start restricting yourself to an interval, there is a maximum value. I made that very, very difficult to tell, but there's a maximum value there, a minimum value there. So we only really look for absolute extrema when we're on a closed interval. Otherwise, we're just interested in relative extrema. All right. And so just like I should have written this. So pi over 3, that's a min, a relative min, and a relative max. I just wanted to save as much space as I could down here for our picture. And because concavity changes at pi and g is a nice function, g is just trigs and polynomials, so it's great. That's going to be an inflection point. So there's going to be an inflection point at g of pi, which if you just take my word for it, that's going to be pi, so that's 3.14. So we have an inflection point at pi, comma, 3.14. Technically, it's pi, but our y scaling is going to be based on integers. Our x scaling is going to be based on angle measurements, and you'll see that in a second. All right. Any questions on anything we got so far? Alex, yes.
Oh, wait, there's the. Yeah,
So remember, we're plugging into the original function. And so you're going to get pi minus 2 times sine of pi. 2 sine pi is 0. So it's just pi. And then because we're making all of our y values in actual measurements, not angle measurements, I'm going to leave it as 3.14. But you can leave it as pi. So, any other questions? We're-
Oh, I didn't get that by just plugging it in, or like, what makes that inflection?
So that's because the concavity changed. It went from being concave up to concave down, and the function was defined there. So we're only working on the interval from 0 to 2 pi. So we're only working with the right half of the plane. We don't need to worry about the left half. So we're going to draw our graph for just mostly the first quadrant, but a little bit in the bottom quadrant, the fourth quadrant. So I'm going to do that. Now, so whenever you have a trig involved in your equation, in a function, you should probably make your x intervals angle measurements, just like you would do with a normal trig function. If you guys remember from 127 graphing trig functions, you took it and you split it up into 2 pi, and then you did like pi over 2, pi, 3 pi over 2, and so on and so forth. We're going to do something similar. So we're going to put 2 pi over here. We need to have pi, which will be right in the middle. We need 3 pi over 2, or pi over 3, which is roughly about there. Because that's 1/3 of a pi, so it should be roughly 1/3 the way there. Because right, 1 pi over 3, 2 pi over 3, 3 pi over 3. And then 5 pi over 3, that's just 1 pi over 3 less than 2 pi, so it's going to be right around here. It does not need to be perfect. And trust me when I tell you, if this problem were to come up on the exam, I would give you a nice neat grid. Yeah, I would give you the grid that you would want to use. Yep, 5 pi over 3. All right. So, and then we noticed that the largest y value that we had, if you look at all the points that we were given, the largest y value we had was 6.97. So our y values should go up to about 7. and go down to about -1 because the lowest y value we have is -0.68. So we'll make 7 tick marks up top, 1 tick mark, 2 tick marks down bottom. 1, 2, 3, 4, 5, 6, 7. I've been teaching math for 15 years at this point, and I still have to count it whenever I make tick marks. So just want you to know, I'm one of you guys. All right, let's pull out all of our points first. So we had 0, 0. We had pi over 3 comma -0.68, so roughly about there. We had pi and then 3.14, so roughly about there. And then at 5 pi over 3, we're at roughly 7, so right about there. And then at 2 pi, it was 6.28, so dip down just a little bit right about there. Now we could probably graph this based on, like, we have 5 points here. That's enough to usually get the right sense of what it's going to look like. But let's go ahead and make our little little cheat sheet up down the bottom. And we're going to see how good I was. So we're also going to draw those vertical lines. So we're going to see how good Phil was at plotting this on the dotted line without, by freehand. G prime, G double prime. G prime had pi over 3 and 5 pi over 3. And G double prime had just pi. Positive here, negative here. And then it was decreasing, increasing, decreasing. So use your cheat sheet or think about it as you go along. You'll see that the curve ends up looking like, just to save on time, bends this way, then up, then bends down as you move left to right, and then bends down further. So let's draw our little vertical lines. That one I did well. Pretty well. Pretty well again. Not well. Wait, that line isn't straight, is it? Bugging me. Good enough. I promise you, once again, you will have a nice, neat grid if there's any problem like this on the exam. So we can use our little cheat sheet down below to kind of get the sense of what the graph should look like. It should look like this. Isn't that a pretty graph? In fact, as just an aside, just to maybe add a sense of wonder, trig can be very, very fun when it comes to when it comes to graphing. So if you'll notice, by the way, the curve y equals x looks like that. So in fact, actually, if you were to graph this whole function, x minus 2 sine x, everywhere, what the function ends up looking like, it's very pretty. It ends up looking like this. Yeah, here's y equals x. And the function ends up looking like this. Wait, let's start with that. Right? And in fact, there's all sorts of fun ones you can do. If you do, if you look at the function x equals y equals x sine of x, like this, the function ends up looking like this. Here is y equals x, positive y equals x. Here's y equals negative x. this curve ends up looking like this. And it's because sine is bounded between 1 and -1. So it just oscillates the x values between positive x and negative x. If you do y equals x squared, you end up getting this curve. So here's y equals x squared and y equals negative x squared. So if I make this, x squared sine of x, the curve ends up looking like this. So just fun stuff, fun, cool stuff. Something you study a lot in differential equations late, like much higher differential equations. Trevor.
So for pi over 3 and for the point pi over 3, 0.68, is it 0.68 or is it negative 0.68?
It was negative 0.68. Did I write? Yeah, negative 0.68. Okay. All right, and so I will provide a recording of this one here. This one has to do with slant asymptotes, if you remember those, or oblique asymptotes. Sometimes it's called oblique asymptotes. Video on that later. But you can still have slant asymptotes involved in the problem, so we'll get to that later. And instead, we'll go ahead to optimization. And sorry, we're going to go straight through. We're not going to take a break, unfortunately, guys. Try to, but just I like to waste more time. I want to just mention you guys have been an excellent class this entire semester. You guys ask the best questions. It's why I love teaching calculus, but you guys have been like, it is why we were behind, but I love answering questions. So I really appreciate you guys asking all the questions that you do.
That's also figured out our laugh at your dream.
Say what?
That's also laugh at your dream.
Oh yeah, the other class does not. And they won't be able to see this because this is hidden to them. So, all right, optimization, an actual real life application. Now, once again, fair warning, we're dealing with single variable mathematics. We can't go to the multivariable case yet. And most things in real world are not single variable. There's multiple variables, things that you're trying to do. But this gives you a sense of what is to come in next classes. What you'll learn in 283 are things called Lagrange multipliers, which is taking a bunch of constraints and trying to maximize or minimize something. So the most classic example that I can think of is trying to fit the largest box inside of an ellipsoid. So not like a sphere is like a three-dimensional circle, an ellipsoid is a three-dimensional ellipse. That was one of the questions that I got asked in my calculus 3 class. It's always fun. Say what? Like an egg or a pill capsule. Yeah. And so it's asking you try to figure out the maximum rectangular box that you can fit into it. And depending on like how much the curve bends, it changes everything. And so those are like, it doesn't seem like it would be, but there's a lot of things that you can do with Lagrange multipliers. Obviously, that's a little bit beyond the scope of our knowledge at the moment, but you will get there. There are many things that you can do, but we're going to learn the first derivative, the first case of just dealing with single variables. So the approach, because these are going to be word problems, everyone's favorite, I know. And the other thing I will mention, and this is the reason why I have put this in chapter 3 versus chapter 2. A lot of students will try and get related rates and optimization mixed up. These are like, optimization is completely different because it's dealing with trying to optimize, to maximize or minimize something. That's why we had to wait until now to do it. So step 0 is to read the problem very carefully, just like normal. Make sure you take time to digest all the information. It is very easy to get the related rates problems and the optimization problems mixed up. But the key thing to look out for, to know which one you're dealing with, is if you see optimize or maximize / minimize or largest / smallest, any of those words that would be used to try and talk about a largest value or a smallest value, something that you're trying to make the largest thing of the biggest thing, that would indicate an optimization. So if you do not see like find the maximum value, if you do not see it, it's probably related to Brake's problem. If you see find the maximum area, that's a dead giveaway that we're dealing with optimization. Step one, as per usual in my course, if you can draw a picture, and you'd be surprised how useful it can be. It really helps. It can give you ideas on where to go. Step two is to write down the relevant information, not relative. There are typically two equations that you get in an optimization problem, specifically for us, because we're only dealing with usually just dealing with one variable and then a second variable that we write in terms of the other. Typically, you get two equations. One of them is called the optimizing equation. The optimizing equation involves the quantity you want to optimize. Sometimes it has two variables. Quantity, yes.
Quality matters too.
Quality does matter, but in this case, we're always going to be measuring things based on quantity. So that's why we're going to be wanting to deal with how to, like, this function will have, like, this equation or function will deal with the quantity that you're trying to optimize. Sometimes it has two variables. If so, you use the bottom of the next equation to substitute. So that's the optimizing equation. It's the thing that you're going to use. This is the thing you're going to take derivatives of, because you're trying to optimize, meaning you're going to be using the first or second derivative test to define maximums and minimums. The next one is what I like to call the constraint equation. I'm underlining these because these aren't exactly definitions. These are terminologies that I have written. Some books use optimizing and constraint equations, but it's not a generally accepted term. That's why I'm underlining it in red instead of writing in red. But these ones usually involve a quote unquote bound, which will allow you to write one variable in terms of the others. So it's usually like you want to maximize area, but you're working on a circle. So there's going to be two variables that like circle has like a radius, but it has X and Y values, right? Because there's all the points on the XY curve, the circle curve. So that's what you're talking about. That would be a constraint, and you'll see it more once you get there. Yes, Paul. Constraint.
Constraint.
Yes. Constraints. Constraint equation. It's the thing that kind of limits your abilities, because like that's how most optimization works, right? You're trying to, like, if you want to think of it in a capitalistic way, you're trying to maximize profits while minimizing costs. So you're trying to, like, maybe you can only produce X amount of objects, and it's based upon two different variables. Now, step 2.5 is that if you have a constraint equation, use it to make a substitution into the optimizing to create a function of one variable. So If you have X's and Y's in your thing, then you can make X in terms of Y by your constraint equation and then substitute that in, and now you have a function that's purely in terms of X or purely in terms of Y. Step 3. So now, ideally, after step 2 or 2.5, your optimized equation should be only one variable. And if that's the case, you're going to optimize it by taking the derivative and finding the critical points. First or second derivative test works. First or second derivative test is fine. You can either use the first derivative test or the second derivative test to find out where the maximums and minimums occur. Since we're not talking about, like, optimization is not talking about when your product, when your area is increasing or when your area is decreasing, it's purely when you have maximum or minimum area. You don't need to find the intervals of increase and decrease. But if you use the first derivative test, it will, like, it'll just do that automatically.
We do one of these kind of with the computers.
Kind of, yes, but that was the one that was an absolute extreme one. So, like, and that one didn't have a constraint equation. It already gave us a function. But yes, that was an optimization problem as well. And then step 4 is to answer the question completely using your solution from step 3. Sometimes it's like trying to maximize dimensions of like a square. When you do part 3, you're going to get one value because you're doing a single variable equation. That only gives you one of the dimensions. You need to find the second dimension. And so on and so forth. Now, the thing I mentioned in step 3, by the way, is make sure you test the endpoints if you're on a closed interval, i.e. the absolute value, the like absolute extrema, not absolute value. And then be sure to verify that it is a max or a min. I will mark you down if you don't. Because sometimes students will only get one value, one critical value. And they'll say, oh, well, that's got to be it. Yes, probably will be. 9 times out of 10, it will be. But if you're building a bridge, you don't want to just leave that to chance, right? That's how we get some bad infrastructure. So answer the question completely. Make sure your answer makes sense. If you can only use 9,000 feet of fence and your answer gives you 10 billion, probably did something wrong. So the most classic example that almost everyone experiences as their first problem is a ranch has 200 feet of fencing. That 200 feet fencing is not a lot of fencing, is it?
Not really.
No. You can tell I'm not a farmer. I don't have a green thumb at all. A ranch has 200 feet of fencing. Maybe I should say something different, maybe 200 miles. Either way, suspension of disbelief. A ranch has 200 feet of fencing for which it wants to enclose 2 adjacent rectangular plots that will share a common fence. What dimensions should be used to maximize that enclosed area? Oh, I did. When I did this originally, I did something different. It's fine. All right. So we've read the problem. We now have to think about how to draw a picture. A picture is worth 1,000 words here. So we want a rectangular plot. And we want it to share a common fence. We're going to divide it up into 2 pieces. So maybe we have our chickens over here. And we have our cows over here.
I love that chicken.
Thank you. Looks like a chocobo.
It does look like a chocobo.
So, not that I know what that is.
Totally
But
not.
anyways, so that's the picture. Now, how do we figure out? We want to maximize the area. So we want to maximize the dimensions. So let's just call this right here. Let's call the pen is dead. Really? Okay, wonderful. We're just gonna have to wait for a second and talk about it. How pretty is my drawing right there?
I like it.
Well, thank you.
It's a Picasso. Yeah,
Uh,
your car doesn't have spots.
okay. Are you kidding me? Those are horns.
I could, yeah, I could own that dog. I was gonna say that.
Well, okay, fine. We have a dog farm. I don't know.
Or he could be herding the chickens.
Oh, it is time to go. Okay, never mind. So, well, we were saying, like, I guess the pen was just trying to tell us it was time to go. Okay. All right, guys, we'll pick up next time with that. I'll give you an update on the exam review and everything, with an email later today. Yes.
Test Wednesday, no quiz.
Yeah, test Wednesday, no quiz. Yes.
You need to type right now.
Yes, please bring your exam redos to the front. If you took it back for anything. And hope you guys have a lovely weekend. If you have any questions, feel free to talk, feel free to email me. Otherwise, you guys have a lovely day. See you then. Thank you.